Redox reactions, we're talking about two separate reactions. We're looking at oxidation and reduction. The main thing that we need with oxidation and reduction, the only way to recognize whether it has occurred or not, is to track and look at oxidation numbers. Remember that oxidation numbers are simply a way to track electrons and notice whether a change has occurred. And the sole reason we track electrons is to know whether redox has occurred. Now, redox occurs either as oxidation or reduction. You have to have one versus the other. To the mnemonics to remember what does what are oil rig and Leo goes grr. Oil rig, oxidation is loss. Okay, oxidation is loss, reduction is gain. Leo goes grr, lose an electron oxidation, gain an electron reduction. The other thing to remember is that if I lose an electron, my oxidation number increases. It gets higher, it gets more positive. If I gain an electron, my oxidation number decreases. It's reduced. So come up with some kind of way that's going to let you remember that. When we look at displacement reactions, and when we look at two elements forming a compound, the oxidation and the reduction are obvious. You see that change in the redox number, the oxidation number for redox. So I have something that gains electrons, I have something that loses electrons. It's very obvious. Remember that metals, elements, have an oxidation number of 0. So if I go from 0 to positive 2, it's oxidation. If I go from a positive to 0, it was reduced. Now, the importance of this is to recognize that not every reaction that goes in one direction can be reversed. In other words, copper will replace silver in solution, but silver won't replace copper in solution, and this is because of the activity series. The activity series is strictly based on the oxidation side of our reaction. Activity series basically means what is the natural trend, which ones are more reactive, which ones are more likely to lose electrons. And so this is what our activity series is based on. So the easiest metals to oxidize are at the top, the hardest ones are at the bottom. So it's much easier for lithium to lose electrons than it is for gold, platinum, or mercury. And that's why we care about the activity series. Now, in terms of what we're talking about with the activity series, the thing to remember is that, again, this is just 1/2 of our reaction, because we said if we have oxidation, we have to have reduction. So when we talk the activity series, we're dealing with oxidation. When we talk about reduction potentials, obviously we're talking reduction. Notice that I can put a charge to reduction potentials. The other thing is to look here. See how lithium has the most negative reduction potential, but it was the easiest to oxidize, and that kind of makes sense because they're opposite reactions. Reduction gain, oxidation loss, and so that makes sense. And so when we talk about the reduction potentials, that's what we're talking about. Now, balancing redox reactions are based on the half-reaction method. In other words, only on paper, because we know where one is, the other is, only on paper do we actually separate out the reactions. And this is strictly so we can follow and determine what the electrons are, how many electrons are involved, did we account for all the electrons, were all the electrons lost, actually gained. And this is why we use the half-reaction method. Now, the method I'm going to show you and the method the book shows you, these two steps are what they have in common. We assign oxidation numbers and we determine what's oxidized and what's reduced. Now, the big thing that changes is the book has you do all of this with the half reactions. I don't. We do only this and this when they're half reactions. So we balance the elements to make sure everything's accounted for, and then we balance the charge by adding and electrons to either the reactants or the products. Oxidation is loss. The electrons go in the products. Oxidation reduction is gain. The electrons go in the reactants. Now, these are the rest of what they have you do in the book, and the book takes you through exactly the same sample we're going to go through in the order they give it. I'm giving you my order. You decide which one works best for you. I like this order where we do the charge and the elements as half reactions and everything else after we combine it, simply because it verifies this right here. It makes sure our equation is balanced. So we're going to start. The first thing you want to recognize is that permanganate to manganese, remember that we've dealt with permanganate before. We know that the manganese here has to be +7. We know the oxygen, because oxygen is 2 negative, gives me an overall 8 negative charge to get my 1 negative. So this is how I know that permanganate, the manganese and permanganate is +7, it goes to +2, it has to be reduced. That means that it's my carbon that's actually oxidized. Now, again, we go back. It goes back to being able to count the oxidation number in any kind of a compound. So I have 4 times 8. Let me erase some stuff. So again, I have 4 times 2 negative. That gives me 8 negative as an overall charge. I have to equal 2 negative because that's the charge on the ion. The only thing that will make that true is if I make the carbon 6+. Well, guess what? There's 2 carbons to produce the 6+. That means each carbon is 3+. Now we come over here, we do the exact same process with our carbon dioxide, except it's not charged, so I know it equals 0. 2 times 2 negative gives me an overall 4 negative charge. The only way that this can be equal to 0 is if my carbon here is 4 positive. 3+ to 4+, my oxidation number increased, therefore the carbons is what becomes oxidized. So we see that change, we recognize what's going on in terms of oxidation reduction, and now we split it up. So now we deal with the oxidation half reaction, and when we look at this oxidation half reaction, we know we have to balance the carbons. After we balance the carbons, what we care about is balancing the electrons. So my carbons are balanced. I know I have a 3+ going to a 4+, but I have 2 atoms each, so that's why I have to add 2 electrons to the right side, and I add it to the right side because oxidation releases the electrons. The electrons are a product of the change. Now, within reduction, the electrons are not a product, they're a reactant, they're required. So that's why I have to add them to the left. And again, it has to be 5 because manganese went from 7+ to 2+. Now, here's the deal. Remember that when I deal with and combine half reactions, the half reactions together, I want to make these electrons equal. I want to make them the same value. To make them the same value, I have to have a lowest common multiple. The lowest common multiple of 2 and 5 is 10. So to turn 2 into 10, I multiply by 5. To turn 5 into 10, I multiply by 2. So now we combine them. And again, this is where I drastically diverge from the book. Well, maybe not drastic, but I diverge. And when we add it together, we recognize that I have all of this. I've multiplied the variables all the way through. And notice what's the same on both sides. And what's the same on both sides are the electrons. And if the electrons are the same on both sides, just like when we saw net ionic equations, I get rid of them. So now, to get rid of them, I have to deal with everything else that's left. And to deal with everything else that's left is primarily accounting for oxygens and hydrogens that we haven't accounted for. All of the oxygen in my oxalate is accounted for in my CO2. I don't have any excess oxygen to deal with. However, the oxygen in my permanganate is not addressed. I don't have any oxygens on the product side to deal with it. So this is why I have to add water. We always use water to deal with oxygens. Now the kicker is to remember how many oxygens to add, because initially you might say, well, I've got 4 here, I need to add 4, but don't forget there's this 2 in front of it. So really I need 8 oxygens. So that means I need 8 water. Now as soon as I add water, I've now introduced something else to account for, and that's the hydrogens. Well, I have 8 waters, that means I have 16 hydrogens. The 16 hydrogens need to go to this side, and now I have a balanced redox reaction. All of my oxygens are balanced, all my hydrogens are balanced, I'm good. Now, the big thing to remember is that's in an acidic solution. Well, how do you know it's acidic? Because I have the hydrogen ions. I have these guys right here. So if I want to put it into a basic solution, I have to get rid of the hydrogen ions. That means if I need to neutralize them, anytime we deal with an acid and base neutralization, hydrogen is most commonly neutralized with hydroxide, and so I add hydroxides to eliminate it. So if I come over here and I have these 16 hydrogens, that means I literally need to add 16 hydroxides. Whatever I do to one side, I do to the other. It's kind of like math. So I come over here and I add 16 hydroxides. Now, these together make water. So I'm going to turn that into water, and now I have 16 H2Os. Well, I have 16 H2Os in the reactants. I have 8 in the product. I can eliminate some. So I eliminate the water over here. That changes this to 8 because 16 minus 8 is 8. And now in a basic solution where I've neutralized my acid and I've introduced hydroxide, I have hydroxide and water. That's the only difference. Now again, the reason this matters is because we want to be able to track what's oxidized and what's reduced. Now, oxidation and reduction potentials. Oxidation is activity series, reduction potentials has to do with the ability to produce a voltage, which we will be talking about in electrochemistry. The main thing again is recognize if something's easily oxidized, it's not necessarily easily reduced, and so the more positive, the more positive the reduction potential, the more likely it is that we will experience reduction, the more likely it is that it will gain the electrons. And that's all this is. Now, you don't have to know oxidizer and reducer in terms of terminology. You simply have to know what's oxidized, undergoes oxidation, what's reduced, undergoes reduction. And if you want to know oxidizer and reducer because of that future plan that you have to be on Jeopardy and the trivia that is required, the ers are always the doers. The oxidizer isn't oxidized, it does the oxidizing. So it causes something else to be oxidized. So if I kick something, it's kicked. It's not what, it receives the kick. So the kicker isn't the kicky, is the easiest way I can think of. Okay? Now, again, just keep reduction potential and activity series separate. Reduction potential, literally, the likelihood that it'll gain electrons. Activity series, the likelihood of losing electrons. But both work together whenever we deal with redox, because we cannot have one without the other.